In geometric optics, we consider the simplest model of light, which is that light consists of rays traveling in straight lines. This model is quite inaccurate because actually light consists of waves and not rays, but it is still important to be familiar with ray optics because ray optics is relatively simple, it's intuitive, and it's still good enough for many applications. In complicated optical systems, it would just be too difficult and unnecessary to use the wave model of light, so instead we still use ray optics. We start with a very basic optical instrument, the pinhole camera. So why would the pinhole camera be interesting to us? Firstly, the pinhole camera provides straightforward evidence for the ray model of light, and secondly, it serves as a simple illustration of what it means to create an image of something. Say we have an object, and we want to create an image of it on a screen. Here's what we assume in ray optics. Each point of the object scatters rays of light in all directions. If we look at the light that hits the screen, then we wouldn't be able to see a clear image, because each point of the object would give a very big spot on the screen, so the image is very blurred. But what happens if we put a pinhole between the object and the screen? Now, each point of the object creates a small spot on the screen, and this makes the image more recognizable. If we make the pinhole even smaller, the image becomes sharper. So now that we've seen this, what does it precisely mean to image an object? When we're imaging an object, it means that if we consider a particular point on the screen, all the light that ends up at that point must originate from a single object point. There is a problem though with imaging using a pinhole camera. If we want to have a sharp image, we need a small pinhole. But the smaller the pinhole, the dimmer the image gets, because if we make the pinhole smaller, less light goes through. In order to get a bright image, we need to make sure that lots of rays originating from one object point end up at a single point of the screen. This means that we need to make a diverging bundle of rays converge at one point, which means we need to focus light, and we can do this by using a lens. So let's see more precisely how a lens creates an image. Let's start with a thin convex lens. A convex lens is a lens that focuses light, so it makes bundles of rays converge. We can define the focal point, which is the point in which a bundle of rays that are parallel to the optical axis converge to. In case the rays are at an angle with the optical axis, they will not converge at the focal point, but in a point that lies in the focal plane. If the bundle is convergent, it will focus before the focal point, and if the bundle is divergent, it will focus behind the focal point, or it will still diverge even after the lens. To see how we can construct an image in general using a convex lens, let's introduce the following ray tracing rules. Rays that pass through the center of such a lens go straight through without being bent. Rays that are parallel to the optical axis will go through the back focal point. Rays that go through the front focal point will exit the lens being parallel to the optical axis. We can now see that all the rays coming from one object point end up going through a single image point, thereby creating a clear image of the object. This image is called a real image, which means you'd be able to project it on a screen. We call the image real because there are real physical rays of light traveling through it, which is, as we're about to see, not always the case. Now let's see what happens if the object lies between the front focal point and the lens. If we now apply the ray tracing rules, we see that the transmitted rays will not intersect, so no real image is formed. However, if we were to extend the transmitted rays, they would intersect in front of the lens. Note that there are no actual physical rays intersecting, only so-called virtual rays. Therefore, there is no real image, but rather there is a virtual image. At this point you may wonder, why do we bother defining an image that is not real, through which no real rays are traveling, but only imaginary virtual rays? In order for any image to be of any relevance in the real world, should it not be a real image? And the answer to that is, yes, ultimately we care about forming real images. But virtual images are important to consider because they describe how real rays, even though they're not forming a real image, have the potential to form a real image if another lens were introduced. For example, consider a magnifying glass. If used properly, it will not create a real image but a virtual image. But this virtual image is useful because it means that the real rays travel in such a way that the lens in your eye can form a real image on your retina. And so it's as if we are seeing the imaginary virtual image as if it were an actual object. And the same idea goes for other optical instruments such as microscopes, telescopes or binoculars. They create virtual images that we can see as if they are actual objects, because the lens in our eye turns the virtual image into a real image. So we have seen real images, through which real rays travel, and virtual images, through which imaginary virtual rays travel. We have seen that a virtual image can serve as an imaginary object for a second lens. So we can define this object as a virtual object, because it is defined by virtual rays as opposed to a real object that is defined by real rays. We have seen that the image created by a lens, which is either real or virtual, can be on either side of that lens, but our object, either real or virtual, has always been in front of the lens and never behind it. It wouldn't make much sense to put a real object behind the lens because then no rays from the object would travel through the lens. But would it make any sense to define a virtual object behind a lens? Let's consider the following setup. We have an object of which we create a real image using a convex lens. Now we put a second convex lens after the first one. To see how the image is formed in this case, we treat the real image that would have been created with the first lens as an input object for the second lens. This object would be a virtual object since it is defined by imaginary virtual rays, which are extensions of the real rays before they pass through the second lens. So how do we construct the image of such a virtual object? We can draw a virtual ray from the virtual object through the center of the lens, and we can draw a virtual ray parallel to the optical axis. Before the lens, these rays are real rays, and with the ray tracing rules we find how they would actually propagate after the second lens. And this way, we can find the image of the virtual object formed by the second lens. Now, let us move on to the concave lens, which is a lens that defocuses light, so it makes bundles of rays diverge. For a concave lens, rays that are parallel to the optical axis exit the lens as if they came from the focal point. Rays that go through the center of the lens are unaffected. Rays that would go through the back focal point exit the lens parallel to the optical axis. By extending the rays and seeing where they intersect, we see that the virtual image is formed. Those were the ray tracing rules for thin lenses. We have seen how they can be used to see where real images or virtual images of real objects or virtual objects will form. Next, let us look at how we can analyze more complex imaging systems. We have seen how we can construct an image if we have an object and a lens, or maybe even two lenses. But what if we have a really complicated system of many lenses? Will we still be using virtual objects and tracing rays to find where the final image forms? In this case, it is more convenient to follow a different approach. Let us start with a single ray that travels for a certain distance. We can define its starting height y1, its final height y2, and the angle alpha it makes with the optical axis. At this point it is important to be clear about the convention that we use here. If the ray travels upwards, the angle alpha will have a positive sign, and if it travels downwards, it will have a negative sign. If the ray is above the optical axis, y will have a positive sign, and if the ray is below the optical axis, y will have a negative sign. We can put the two quantities y and alpha in a vector, and this vector will then be used to describe the ray. In our case, we include n, which is the refractive index of the medium through which the light is propagating. This is also just a matter of convention, and other sources may choose not to include n in their ray vectors. Our goal will be to describe optical systems as matrix operators that act on these vectors. This method is called ray transfer matrix analysis or ABCD matrix analysis. For example, let's see what matrix describes propagation by a distance d. If we start at height y1 and propagate for a distance d at an angle alpha, we end up at a height y2, which is y1 plus d tangent alpha. If we assume that alpha is small, which we call the paraxial approximation, we can say that y2 is approximately equal to y1 plus d alpha. As a side note, the paraxial approximation or small angle approximation is a very important approximation that is often made in optics to simplify computations tremendously. The field of optics in which this approximation is made is called paraxial optics or Gaussian optics. Anyway, returning to our original discussion on finding the propagation matrix, y2 is approximately equal to y1 plus d alpha, and the angle alpha that the ray makes with the optical axis doesn't change after propagating. So we can define the following matrix that describes propagation by a distance d. This matrix says that alpha 2 is equal to alpha 1, and that y2 is equal to y1 plus d alpha 1. Now let's see if we can find the transfer matrix for a thin lens. At the lens plane, there is no discontinuity in the ray because we assume this lens to be thin. So before and after the lens, the height is y. Now what happens to the angle of the ray at the lens plane? Because we want to describe the effect of the lens in terms of a transfer matrix, we assume that alpha2 depends on alpha1 and y1 as n alpha2 is equal to a n alpha1 plus b y1, where a and b are the coefficients we wish to find. To find a, consider a ray that is traveling through the center of the lens. In this case, y1 is equal to 0 and alpha2 is equal to alpha1, so a is equal to 1. To find b, consider a ray that is parallel to the optical axis, that enters the lens at a height y. We know that after the lens, this ray will go through the back focal point for whatever value y we consider. Therefore, the angle alpha2 of the ray after the lens is minus the arctangent of y over f, which in the paraxial approximation can be approximated as minus y over f. Note that there is a minus sign in the expression because if the ray is above the optical axis, which means y is positive, the ray will bend downwards, so alpha is negative. Therefore, b is equal to minus n over f. With these findings, we can now write down the transfer matrix that describes propagation through a thin lens with focal length f. Let's now return to our original question. Given a complicated imaging system, how can we analyze it efficiently? We've now seen that propagation in free space and propagation through a thin lens can be described by transfer matrices. To find the transfer matrix of a complicated imaging system, simply multiply all the transfer matrices of the components. Now suppose we have some transfer matrix A, B, C, D of an arbitrary optical system. How do we extract useful information from it? For example, how do we derive the imaging condition? How do we derive the magnification? Or how do we find the locations of the front focal plane and back focal plane? Let's start with finding the imaging condition. Recall what it means to be imaging something. It means that all the rays leaving from one point y1 at whatever angle alpha1 should end up in the point y2. In other words, y2 should be independent of alpha1. For the transfer matrix, that means C should be 0. Therefore, the imaging condition for the optical system is met when C is equal to 0. Now the next question. How do we find the magnification for the system? In order to define a magnification at all, we must assume that the imaging condition is met, so C is equal to 0. Now we can define the magnification as y2 over y1. We can see that this equals D in the transfer matrix. Thus, the magnification of the optical system, assuming the imaging condition is met, is D. Our final question was, how do we find the locations of the front focal plane and back focal plane? To find the back focal plane, we must consider an incident ray of light that is parallel to the optical axis and see where it intersects the optical axis after the imaging system. An incident ray of light that is parallel to the optical axis is described by taking alpha1 is equal to 0. The intersection with the optical axis after the optical system is described by taking y2 is equal to 0. This yields an equation dy1 is equal to 0. Therefore, the back focal plane is found by setting d is equal to 0. Alternatively, we could consider an object placed at infinity and see where its image is formed. The reasoning to find the front focal plane is analogous. We consider a ray that goes through the optical axis in the front focal plane, and it exits the optical system parallel to the optical axis. This yields the equation A is equal to 0. Alternatively, the front focal plane can be found by seeing where the object should be in order for its image to be at infinity. Now that we've seen how to find the imaging condition, the magnification, and the front and back focal plane, let's analyze a simple optical system. For a single lens system, rays starting at an object propagate a distance d1, then go through a thin lens with focal length f, and then propagate another distance d2. By multiplying the three corresponding transfer matrices, we find the transfer matrix of the system. Note that the transfer matrix that affects the ray first, the one with d1, is on the right-hand side of the multiplication. This is because an input vector will first be multiplied by the matrix on the right. So now let's see whether we can find the front focal plane. To do this, we set A is equal to 0, which gives d1 is equal to f, which is indeed the front focal plane. For the back focal plane, we set d is equal to 0, which gives d2 is equal to f, which is also true. It must be said though that other sources may use a different sign convention. They might say that the front focal plane lies at minus f and the back focal plane at f. For the imaging condition, we set C is equal to 0. This gives an equation that we can rewrite into the familiar lens equation. The magnification is given by D. Next, let us look at some practical applications, namely optical instruments. Many optical instruments aim to magnify objects. Think of magnifying glasses, microscopes, and telescopes. Therefore, it would be useful if we were able to quantify the magnification of an optical instrument. So let us ask ourselves, how do we quantify magnification? One definition which we have used previously is the linear magnification, which is defined by dividing the image height by the object height. This may be a useful definition for real images that are projected onto a screen or captured by a camera, but it's a bad measure of magnification for optical instruments that generate virtual images. The reason for this is that when you look at a virtual image, it is the apparent size of the image that matters, not the actual size. For example, the actual size of the sun is much larger than the actual size of a golf ball, but as long as the golf ball is close enough to your eye and the sun is far away enough, the two objects appear to have the same size due to perspective. Similarly, a virtual image that is really large may still appear really small to you if it is very far away. Therefore, we introduce a measure of magnification that better describes the apparent size of the image in comparison to the apparent size of the object. This measure is angular magnification. A good measure of the apparent size of an object is its angular size. The angular magnification is defined as the angular size of the image, beta, divided by alpha, which is the angular size of the object when it is viewed with the unaided eye. Clearly, the angular magnification is not equivalent to the linear magnification, since it is possible to have different linear magnifications for the same angular magnification. Note that this angular size is not uniquely defined. Depending on how far away you put the object from your eye, the angular size varies. It makes most sense to use the largest possible angular size, which is found by putting the object as close to your eyes as possible. However, if you put the object too close to your eyes, you cannot focus on it anymore. Typically, the closest you can put an object to your eye while still being able to focus on it is 25 centimeters, which is called your near point. So the angular size of the object viewed with the unaided eye can be calculated as alpha, which is equal to the inverse tangent of h over d, where h is the size of the object and d is usually taken to be 25 centimeters. However, for the sake of clarity, we'll just keep using the letter d instead of 25 centimeters. Now let's see what happens when we put a thin lens, which is our magnifying glass, between the object and our eye. We place the lens such that the object lies in its focal point, so that the virtual image is formed at infinity. The reason we do this is because when the eye looks at an object at infinity, it is most relaxed. But of course it's not impossible to put the object at a point other than the focal point. Now we must calculate the angular size of the virtual image. Since the image lies at infinity, and the image is infinitely large, we cannot calculate its angular size by comparing the image height to the image distance. The fact that the image is infinitely large also illustrates why it doesn't make much sense to use the linear magnification to quantify the magnification of the magnifying glass. Rather, to calculate the angular magnification, we look at the angle of the virtual rays that go through the top of the object. This angle is given by beta, which is equal to the arctangent of h over f, where f is the focal length. By applying the paraxial approximation and dividing the angular sizes, we find that the angular magnification of the magnifying glass is d over f, where d is conventionally chosen to be 25 centimeters. Next, let's have a look at a two-lens microscope. Let's assume we have an object with height h, and that the first lens creates a real image with height capital H at the front focal point of the second convex lens, which has a focal length f. What is the angular magnification in this case? Again, we define the angular size of the object viewed with the unaided eye to be alpha equal to h over d, where d is the near point at 25 centimeters. The angular magnification is defined as beta over alpha, where beta is the angular size as seen through the microscope. So how do we find beta? Since the image of the first lens lies in the front focal plane of the second lens, we can use the result we derived for the magnifying glass to calculate beta. In this case, beta is equal to capital H over f. By rearranging the resulting expression, we find that the angular magnification of this microscope is given by the linear magnification of the first lens multiplied by the angular magnification of the second lens. For the final example, let's have a look at a telescope. In this case, the object of interest is very big and very far away, like a star. This means we have to use a slightly different approach to find the angular magnification. For example, we typically don't know the actual size h of the object, and to calculate the angular size alpha of a star viewed with the unaided eye, We definitely don't want to put it at our near point of 25 centimeters. Rather, instead of calculating alpha from h and d, we assume that alpha is given directly. Now for the second point. How will we draw the ray diagram? It seems rather impractical to draw a very large object a very large distance away from our tiny telescope and then use ray tracing rules to see what happens. So here's the distinction we'll make between treating small nearby objects and large faraway objects. For a given point of a nearby object, there will be a wide cone of rays radiating from it. There will be a ray parallel to the optical axis, there will be a ray going through the center of the lens, and there will be a ray going through the front focal point of the lens, and these rays will propagate at widely different angles. On the other hand, for a large faraway object, one object point will give an approximately parallel bundle of rays at the telescope. For each object point, the angle of this bundle of rays will be different. The largest angle will be given by the point at the edge of the object, and so it is this angle that determines the angular size of the object. So, to calculate the angular magnification of a telescope, let's consider an incoming parallel bundle of rays at an angle alpha. These rays will converge in the focal plane at a height H approximately equal to minus alpha times f1, where f1 is the focal length of the first lens. The second lens, with focal length f2, is placed such that the intermediate image lies in its front focal plane, so that the second lens acts as a magnifying glass we've discussed previously. Therefore, we know that the angular size of the object as seen through the telescope is beta equal to H over f2. With these two results, we find that the angular magnification of a simple two-lens telescope is given by minus f1 over f2. So far, we've been ignoring the fact that lenses and optical instruments have finite apertures. Let us next look at how apertures affect the imaging process. Let's say we have an imaging system consisting of two lenses. Somewhere in the system there is a limiting aperture that determines how many rays can go through the system. This limiting aperture is called the aperture stop. It may be one of the two lenses, or it may be an aperture in front of the lenses, or an aperture after the two lenses, or an aperture between the two lenses. For our case, let's assume that the aperture stop is an aperture that is located between the two lenses. How can we quickly find out how this aperture limits the cones of rays that enter and leave the optical system? We define the entrance pupil to be the image of the aperture stop created by the optical components before it. Usually this is a virtual image, but for simplicity let's assume in this case that it's a real image. Recall what it means to image an object. It means that all the rays that leave from one point from the object end up in the same point in the image. Because of time reversal symmetry, we can also say that all rays that go through a certain point of the image of the aperture stop will go through the corresponding point of the actual aperture stop. In other words, any rays that would be blocked by the entrance pupil, if it were a physical object, will be blocked by the aperture stop. Therefore, to quickly see which cones of rays will pass through the optical system, one can construct the entrance pupil and see which rays will go through it. Similarly, to find out which cones of rays exit the optical system, we can define the exit pupil, which is the image of the aperture stop created by the optics behind it. Any rays that get blocked by the exit pupil will be blocked by the aperture stop. Therefore, one can imagine the exit pupil as a physical aperture that determines which rays will form the image of the object. Now let us see how we can efficiently describe the cones of rays that pass through the system. To this end, we'll define chief rays, which so to speak are the centers of the cones, and we'll define marginal rays, which more or less describe the edges of the cones. More precisely, a chief ray is a ray that starts from an off-axis object point and goes through the center of the aperture stop. Therefore, the chief ray will also go through the centers of the entrance and exit pupils. The chief ray indicates the center of a cone of rays and tells us the main direction the bundle of rays is propagating in. A marginal ray is a ray that starts from an on-axis object point and goes through the edge of the aperture stop. Therefore, it will also go through the edge of the entrance and exit pupil. The marginal rays indicate the edge of a cone of rays that is emitted from the object or ends up at the image. Let's look at an example of how chief rays and marginal rays can be used to understand the through-focus behavior of an imaging system. We can draw the chief rays that come from the center of the exit pupil, and we can draw the edges of the cones that come from the edges of the exit pupil. At the image plane, the cones of rays have converged, which results in a clear image. When moving further out of focus, we can see from the chief rays that the size of the image increases. If the aperture stop were a pinhole, then the image would still be clear. However, if the exit pupil has a considerable size, we see that each image point gets blurred when moving out of focus, and the degree to which each point is blurred depends on the rate at which each cone expands. Note that by decreasing the size of the aperture stop, we decrease the rate at which the cones expand, thus increasing the depth of focus of the imaging system. This would also mean, though, that more light is blocked and the image would be dimmer. Let's see if we can now use the concepts of entrance pupils, exit pupils, chief rays and marginal rays to analyze a special kind of optical system, a system that is telecentric. So suppose we have two lenses, whose back focal point and front focal point coincide. The aperture stop is placed at this point. We can now ask the following questions. Where are the entrance and exit pupils? In what direction do the chief rays go? What do the cones of rays look like for different object points? How does the image change when the detector moves out of focus? Let's look at the first question. Where are the entrance and exit pupils? Since the aperture stop lies in the focal plane of both lenses, both the entrance pupil and the exit pupil lie at infinity. They're infinitely far away and they're infinitely large, but their angular sizes are limited. The next question was, in what direction do the chief rays go? The chief rays by definition should go through the center of the aperture stop. Since the aperture stop is located at the focal plane of the two lenses, the chief rays are parallel to the optical axis before and after the system. Then we asked, what do the cones of rays look like for different object points? We know that the edge of each cone should go through the edge of the aperture stop. Since the aperture stop lies in the focal plane of the lenses, the edges of the cone should be parallel to each other outside the optical system. This means that the cone of rays is the same for each object point. The final question was, how does the image change when the screen moves out of focus? If we move the image through focus, the image size remains constant because the chief rays are horizontal. However, the image does get blurrier when moving out of focus. To be more precise, each point of the image gets blurred equally because the cones of rays spread out equally. Until now we have assumed that the thin lenses we consider are able to focus light perfectly. In reality this isn't quite the case. We'll end with a quick comment on aberrations. Firstly, there are chromatic aberrations. This means that the lens has a different focal point for different colors of light. Therefore, if you want to image an object that consists of multiple colors, there may be a problem getting a sharp image. Aside from that, there are monochromatic aberrations, which are aberrations that also occur in the case that light consists of a single color. These aberrations can occur because of imperfections in the lens shape or when the paraxial approximation is violated. Furthermore, there are additional inaccuracies in our treatment of light propagation because the ray model we use is merely an approximation of the more accurate wave model of light. If we take the wave nature of light into account, we enter the domain of diffraction optics.